We're solving problem 4 from the 2018 F equals MA, exam A. A satellite is following an elliptical orbit around Earth. Its engines are capable of providing a one-time impulse of a fixed magnitude. In order to maximize the energy of the satellite, the impulse should be A, directed along the satellite's velocity and applied when the satellite is in its perigee. B, directed along the satellite's velocity and applied when the satellite is in apogee. C, directed towards the Earth and applied when the satellite is in perigee. D, directed toward the Earth and applied when the satellite is in apogee. And E, directed away from Earth and applied when the satellite is in apogee. So here we have a diagram we have a rough diagram of what's happening here. So these are the different velocities, and this angle represents it just represents like how much you would apply if, like, hypothetically, if you did that angle. So, and note that that angle can change, and we want to make it so that we want to maximize the energy of said satellite. So energy is given, initial energy in this case would be 1/2 mv squared minus g m sub e m over r. Now use the impulse momentum theorem. So we get J equals m delta V. So it looks like an O. So then we can find the final energy. So energy final is equal to 1/2 mv plus delta V squared minus gm sub E times m over r. And in order to maximize the energy, we need to maximize the change in energy, or the final energy minus the initial energy. So we want to maximize this. And we can just do this by plugging in these two equations that we just found. So change in energy would be 1/2 mv plus delta V squared minus gm sub E times m over r. And then we this is not here. This is here, the bracket. And then we subtract initial energy, which is 1/2 mv squared minus gm sub E times m over r. Now these two cancel out, and what we're left with is, I'll write it up here, change in energy would be 1/2 mv plus delta V squared minus 1/2 mv squared. Now, what this becomes is 1/2 v squared plus 2 times v times delta V plus delta V squared minus 1/2 mv squared. Now we can factor out the 1/2 and m. We apply the 1/2 to inside the parentheses. We have to divide everything by 2. Notice that when inside of the v squares cancel out. So we're just left with v times delta V plus delta V squared over 2 as our final change in energy. Wait, no. You multiply by mass because you factored it out. So then this can again simplify to m absolute value v times absolute value delta v times cosine theta, this angle theta, and then this is probably too big. Add the delta v squared over 2 and absolute value this. So here we have it. Now, in order to maximize this value, well, let's just think about this. We first want to maximize cosine of theta. Now, we know that cosine of theta is a graph that oscillates like this on the xy plane, where the largest value is 1. So we want that to be 1, and when it is 1, we have theta equals 0, so cosine theta is 1. Therefore, there should be no angle here in order to maximize the energy. So, therefore, we know that it has to be directed along the satellite's velocity, and it's also where it's closest to the Earth. So here we have answer choice A for this problem as our answer.